So now we're going to get into probability and its rules. So the importance of probability is it was originally invented to study games, which is gambling. Many mathematicians studied probability and contributed to it. It helps us make more informed decisions, is why they kind of decided to look at these probabilities and things like that. And the book mentions drinking and driving with this. If you drink, there's obviously a higher probability that you're going to crash. And so if you want to read about that, go ahead and read about it. Consider the following. Suppose we flip a coin 100 times and compute the proportions of heads observed after each coin toss of the coin. The first flip is tails, so the proportion of heads is 0 out of 1, which means 0%. The second flip is heads, so now the proportion is 1 out of 2 of the flips were heads, which is 0.5. The third flip is heads, so now the proportion of heads to tails is 2 out of 3, so 66%, and so on. Plot the proportion of heads versus tails and the number of flips obtained in the graph. We repeat the experiment with the results shown in figure 1b. So we've got two graphs. Obviously, you can see that on the left, those are the actual flips and about what happens. So they're clearly getting a lot more heads in the beginning. And then as they get tails, it comes down some. But if you look at the proportions themselves, remember the first one was 0. The second one, I wonder why they have that 1. That should be number of tails. Because, right, the first flip is 1. I don't know. I don't see 0 plotted on this one, but 0 out of 1 would be 0. So, anyways, if you look at the proportions, though, it sort of, goes a different direction a little bit. We can kind of see that it kind of comes down and goes up and goes down below and then back above. And what we're actually seeing is called the law of large numbers, which we'll talk about here in a minute. We have probability, which is just the measurement of the measure of likelihood of a random phenomenon or chance behavior happening. Experiment is any process with uncertain results that can be repeated. A sample space is a list of all possible outcomes for a particular experiment, and an event is the collection of outcomes from a probability experiment. We have theoretical probability. This is the probability that you think of in your head, and you think, oh, well, if this happens, this is what should happen. And then you have experimental, which is when you actually do an experiment with that probability and see if the results match the theoretical. The law of large numbers says that when an experiment is considered, we typically can use theoretical probability to predict the outcome of the experiment. Flipping a coin should yield roughly the same amount of heads as tails. And consider that experimentally we flip a coin 10 times and we obtain 10 tails and 0 heads. We find it odd that we obtain 10 tails, and so we decided to flip the coin 1,000 times and obtain 400 heads in the experiment. The law of large numbers states that as the number of repetitions of a probability experiment increases, the proportion which a certain outcome is observed gets close to that probability of the outcome. So what that means is, if we suspect that there's going to be a 50% chance it's heads, and we observe early that it's not the case that it's that as we continue doing the experiment over and over, it should get closer and closer to 50% as we do it infinitely many times. Well, not infinite, because you don't want to just keep doing it. But as you do it many times, you should get close to what theoretically should happen. If you don't, then you think that, hey, this thing might be rigged. This coin might be favor one side more than the other. Okay, notation and labeling. So probability, if you see the P and then parentheses E, that's the probability of event E happening. A sample space is a set, so we use the set brackets. And then an event is E sub 1. It says a probability experiment consists of rolling a single fair die. Identify the possible outcomes of the experiment. Determine the sample space, and then define the event E. Okay, so we're going to do that real quick. And the show. So first thing first, fill in these the events, the possible events. So let's look at that real quick. Possible events. E1 is rolling a 1. Next one is rolling a 2. E3. 3. Rolling a 3. What the heck did I just write? Rolling a 3. E4. E5, E6. I am just going to put ... And that just fills in the rest of them. So rolling a 1, rolling a 2, rolling a 3, 4, 5, or 6. Okay, that's our event. So we've done part A. The sample space. Well, that's really simple. If we're going to do the sample space, this is part B. Then that's equal to 1, 2, 3, 4, 5, or 6. Whatever the events are that you can have happen, or whatever the outcomes are. Okay. And then part C says define the event E rolling an even number. Well, that's really simple. Then E, if it's rolling an even number, is only those even numbers, 2, 4, and 6. Okay. And so we're done with this. Alright, so next. Notation. P of E is the probability that event E occurs. The rules of probability are the probability of event E, P of E must be greater than or equal to 0 or less than or equal to 1. That is, 0 is less than or equal to P of E is less than or equal to 1. That makes sense because you can't have over 100% chance of something happening in probability, and you also can't have a negative chance of something happening. It either happens or it doesn't. The sum of the probabilities of all outcomes must equal 1, so that is, for instance, if you're rolling the die, you have a 1 in 6 chance to roll any one of them, and so each one of those individual outcomes is a 1 in 6. So if you add all those together, there should be a 6 of 6 chance, and there is. Excuse me. Next, we have definitions. Probability model. A list of all possible outcomes of a probability experiment and each outcome's probability. We have impossible. If an event is impossible, then the probability of that event is 0. Certainty means that if the event is a certainty, then the probability of that event is a 1. An unusual event, an event that occurs at a low probability of occurring, typically an event with 0.05 or 5% chance occurring. There are times where this should not be used. For instance, if you're finding that cancer rates are lower than 1% and all of a sudden, or let's say that there's something going on and a 5% chance is considered high for it, then I brought up cancer because you wouldn't want a 5% cancer rate among anybody, I don't think. I don't know if there is a 5% in any type of cancer, but there might be. But you don't want that to occur, and so 5% is not always the marker. Sometimes it might be lower, sometimes it might be higher. It just depends on what it is you're talking about. Suppose the probability you're wrongfully convicted of a crime and sentenced to the death penalty is 3% chance. This is clearly less than 5%, but is rather high considering the consequences. We would want the probability to be very close to 0 in this instance. So, right, you don't want to be wrongly convicted of a crime. That's another example. On the other hand of the spectrum, you want to plan a picnic with a 3% chance of rain, and rain is unusually unlikely on this day. So if it's only 3%, you're banking on it not raining that day, and if it did happen, you'd be really surprised. The idea is selecting a probability that separates unusual events from not so unusual events is subjective, so keep that in mind. Is this a probability model? So, allow the class to determine whether it satisfies rules 1 and 2. So, rule 1, are these all between 0 and 1? The answer is yes. And then do they add up to 1 in total? So 13 plus 14. So let's do it. It's 13. I'm going to use my calculator. 13 plus 14 plus 13 is 24 plus 20 plus 16. Yes, it adds up to 100, which is 1 if it was probabilities, and therefore it does satisfy the probability model. Computing in interpreting probability empirical method, the probability of an event E is approximately the number of times that event E is observed divided by the number of repetitions. So it's the number of favorable outcomes divided by the total number of outcomes. So an insurance agent insures 182 teens. Last year, 24 teens had to file a claim on their auto policy. Based on these results, the probability of a teenager will file a claim on his or her auto policy in a given year is, determine the probability. So the number of ones who had to file a claim are the favorable ones in this case, because that's what they're asking for. So 24 people made a claim out of 182. So if we divide that, that is 0.1319. So 13.1% chance that happens. So there's basically, you could say, another way you could say it is about 1 in 10 made a file on their claim. Obviously it's a little higher than that, but close. The next one, the data on table 2 represents the results of a survey in which 200 people were asked. Use the survey data to build a probability model. Okay, so let's do that. We're going to clear this. Actually, what I'm going to do, I'll restart the video. I'll stop here. We'll finish the rest of the slides on the next video. Thank you, guys.